Hi guys, here we go with some more videos. So after reviewing those videos that I created the other day, I wasn't very happy with the quality, so I went out and bought a webcam, and hopefully this works out a lot better. I still feel like I've got a shadow there on the whiteboard, but let's give this a try. So now we're moving on to placing a capacitor in the AC circuit. So I'm going to be working off of the handout. So if you haven't gone to Blackboard and taken a look at this PDF and hopefully printed it off, hit pause right now, go and get this particular handout, the capacitors, which is lesson 2, and let's work along on this together. Everybody back? Everybody's got this in front of them? Okay, so let's continue. So we've spent lots and lots of time figuring out Ohm's law calculations with a resistor in a DC circuit. We can do the very same work in an AC circuit. If it's just a resistor, it doesn't matter. Now we've drawn some triangles looking at what happens when we place an inductor in an AC circuit. Now we're going to look at what happens when we place a capacitor in an AC circuit. So for starters, it would be easy to say that a capacitor is just the exact opposite of an inductor. Okay, so if we just say that and we carry on and do the math, everything will work out nicely. But maybe we should take a minute and figure out just what that means. So let's go back and review. We've already learned about capacitors. Okay, we went through this lesson. What is it? It's got two plates separated by a dielectric. These plates have the ability to gain or release electrons, which means that they can build up a charge. So it takes time, though, for this charge to build, right? So this is the RC time constant. So there's a growth curve, right? So it takes time for this charge to build on the capacitor, okay? Now, so this is voltage over time. If we're measuring the voltage, the potential difference across the two plates of the capacitor, okay, at the moment that we close the switch in a DC circuit, we see this charge start to build, and it takes 5 time constants, depending on variables, the amount of resistance in the circuit, for current to flow for the buildup of the charge. So the fact of the matter is, current is doing the exact opposite. So if this is a DC circuit, this is the moment that we close the switch in the circuit, and it takes time for the voltage to build, for the potential to build on the two plates of the capacitor. So what's happening to current during this same period of time? If we plot current on this same graph, the moment that we close the switch, we're going to have current in the circuit, and we're going to get a reduction in the amount of current in the circuit until we reach the point where we plateau, the capacitor is charged, there's no longer any current flowing. Okay, so here's where this all goes, and I'm just going to throw the statement out there, and then we'll try to wrap our heads around it. Okay, so we could say that the current leads the voltage, okay? Because initially we have current flow, and then the current flow drops off as the voltage builds, okay? So remember, in the circuit with an inductor, okay, and the moment we closed the switch, we immediately had voltage. The potential was there, but it took time for the current to build because the magnetic field of the inductor opposed that growing current. And so it took time for the current to grow, even though the voltage was there immediately. So we said that the current lagged the voltage. Now the opposite is happening. Immediately we have current, okay, but it takes time after the current starts to flow before we see the result, which is the voltage, the potential built up, the charge built up on the capacitor. All right? So we have the exact opposite, okay, as a result. We say that the current leads the voltage. There's current initially, and the result following is that we see voltage in the circuit. So if we look at the handout, okay, we've kind of been going through this, right? We've got the growth charts here on page 3. Here's the AC sine wave as a result on page 4 of the handout. So that we can see we have the applied voltage, there's our typical sine wave, okay, starting at 0 degrees. But if we look at the current waveform that's plotted there as well, we can see that it starts at 90 degrees. Sorry, it starts at its positive peak at 0 degrees, falls to 0 current flowing at 90 degrees, okay? And so the current leads the voltage by 90 degrees in a capacitive circuit. Okay? Now, the next thing I want to talk about, I think I'll pile this all into one video. Actually, no, maybe I won't. Let's just stop it right there.